Hi everyone, let's continue. Let's talk about the line integrals of vector fields. So we can imagine it's like a work along a path. Have you learned work in physics? So when a constant force F is applied to an object that is moving along a straight line with displacement vector given by D, then we define the work done as follows. Okay, so we have this is D. Okay, that is the displacement. And if F is the force, then the work done is F dot D. You can think of, so let's say if this is theta, if the force, so what is the component of the force in the same direction as the D? Well, that component is the force times cosine theta, right? So work done equals the force times displacement, right? So that equals the component of the force in the direction as the displacement times the magnitude of the displacement. And so this small dot, I mean multiply, okay, it's just number multiply, and then this guy equals the dot products of two vectors. So far so good, everybody? Okay, let's look at the following example. A particle in the xy plane is dragged along the straight path from the point P20 to Q51. When we apply a constant force that is represented by the vector 5,3, find the work done on the particle. So first, let's figure out what is the displacement. We use Q minus P. 5 minus 2 is 3, 1 minus 0 is 1. So then the work done is F dot PQ 53.31. So we multiply each coordinate respectively and then add them up together. 5 times 3 plus 3 times 1. 5 times 3 is 15, 3 times 1 is 3, so the answer is 18, right? I know sometimes looks like abuse of notation. This is that. Okay, my bigger dot is like the vector dot product. My small dot is just multiplication of numbers. Is that okay? Yeah, dot product, and this is multiplication of numbers. I know it kind of. So do you remember when we were small, right? When we multiply, we use this notation, and then when we grow bigger, we learn variable x, y, z, right? Then this guy will be confused with the x, right? Then we say, oh, we don't write 5 cross 3 as the multiplication. We write 5 times 3. Even though sometimes it could be confused if you put your dot down there, it looks like 5.3. But now we have the dot product and cross products. So sometimes it's confusing when we use cross or dots, okay? But you know, because those are numbers, then we mean it's multiplication of numbers. Or maybe another way, you can use parentheses. Then this also means multiplication. But wow, it takes a lot of parentheses sometimes. Okay. So just some notation. All right. So I use little dot for the multiplication of numbers, and I use the bigger dot for dot products. So far, so good, everybody? Okay. Okay, now what if the force varies throughout the trajectory? Or what if the trajectory is not straight? Okay, so the work done by a vector field f of xy along a path gamma of t. Okay, in here we have two formula. One formula is in the xy plane, the other one is in the space. Okay, let's look at the formula in the plane. In general, we may apply a force f of xy equals to, so this is a vector value function. It's from R2 to R2, right? The component functions f and g, they are now scalar value function. Okay, so suppose we apply a force on a particle that's moving along a path c, parameterized by a vector value function gamma of t, r of t, doesn't matter, okay? With a less than or equal to t less than or equal to b. Suppose t, so t is a unit tangent vector of c consistent with the orientation. So what does that mean? So this means here we have this curve c right here. Let's say the orientation is like that, and then t is consistent with the orientation. Okay, that c, t is the unit tangent vector. Then the work done by f along c is defined as the following integral. Okay, so we have f dot product with t. Okay, so this is the unit tangent vector. Okay, and this guy equals f dot, this is like the derivative of the displacement, right? Okay, so why they're the same? Okay, let me recall what is the unit tangent vector. Right, the unit tangent vector is the tangent vector over its speed, right? The magnitude of it. Well, that is the gamma prime of t, the derivative of the displacement, over gamma prime of t magnitude, right? And we also know ds dt be this is the same as the v, right? Okay, that's the outline parameter. So now that is why we can replace this guy by ds dt. So this is gamma prime of t, and this is ds dt. So far so good. And furthermore, gamma prime of t is like d gamma over dt over ds dt. So sometimes if we want to get rid of dt, then this is just d gamma ds. So that's why we get t ds equals d gamma. That's why those two are the same. Okay, and let's see, this guy, why they're the same is from this part. Okay, so then we have t okay, we don't need to look at this time. This is because dr is gamma prime of t dt. Okay, so we're using this fact. And then now this is how we calculate. Okay, we have f is remember, f is the vector field, that's f and g are the components, and we dot product with gamma prime of t, which is x prime of t and y prime of t dt. So keep this in mind. Okay, so integral f times dx plus g times dy, but we usually just use this guy. So given a vector field and a curve c, first we need to find a parameterization for the curve c, and then we want to find the velocity vector. Okay, and then we just use this formula. So this is the formula we're gonna use. Okay, let's continue. So mathematically, this is often called integral of the field along the path C. And in the space, we have similar things, except now we have one more variables. Okay, so in this case, f is fgh, and then gamma of t is x, y, z. So far, so good, everybody? Okay, now let's continue. Let's look at some examples. Let's continue. So why is the work integral formula correct? Well, imagine we partition the curve into pieces. So suppose this is the curve C. We gonna partition into pieces. If the pieces are small enough, then each piece is approximately by a straight line segment, right? Each piece looks like a small line segment. Right, like a small line segment. Consider one small piece, and suppose it corresponds to an increment change of t in the parameter. If the piece is small enough, it is approximately by the displacement vector. Okay, so change of the displacement is gamma of t plus change of t minus gamma of t. Then the approximate, so the displacement is change of gamma. Okay, that is displacement. And then the approximated work done, okay, the work along the small pieces. We remember we have from the previous example, if we have the work, the force apply on like a straight line, then we just use F dot the displacement. So now we have the same thing. We have the change of the work is F dot the change of the displacement. Well, the displacement change of r is just like r prime of t dt. Okay, so the approximate work done, we sum all those small work done together, so we get this formula and take the limits as the pieces shrink. Then we get the exact value of the work done along the path. So we have f of t, and then this is dot product with the gamma prime, the velocity, okay, and then dt. So far, so good, everybody? Okay, so here we have some basic properties and interpretations of the integral. First, reversing the orientation change the sign of the integral. Okay, so remember, if we reverse orientation, then our tangent vector will get a negative sign in front of it. Okay, so that's why we just change the sign. Second, if the curve C is made up of multiple pieces, let's say C is like C1 union C2, then we can split the line integrals. Okay, so we can split the line integral on C1 plus the line integral on C2. Okay. Oh, by the way, yes, they also call this line integral as path integral. So they're the same thing. Okay, this is the same as line integrals. Same thing, same name, same thing. So the path integral has usual additive and multiplicative properties. So if we have the vector field, we can add it together. Okay, we can like split them with distribute. Okay, distribute the vector field, and for if we have a constant multiple, we can also pull it outside of the integral. Okay, if F is a force field, then the path integral represents work done by F along the path C. If F is a fluid velocity field, and then the path integral represents the circulation or flow of the fluid along the path C. The circulation of F along C is a measure of how much of the vector field points in the direction of C. Okay, so this is very important. Later on, we will talk about floods. Okay, so I will do a comparison later. So circulation or float measure how much of the vector field points in the direction as the path C. Okay. Now, example time. Let F be a velocity vector field of a fluid. Let C be a curve consisting of the parts of the unit circle in the first quadrant, together with a line segment from -0, 1 to 1, 0. Okay, let's look at the picture. 0, 1, where is 0, 1? Oh, 0, 1 here to 1, 0. Okay, 0, 1 to 1, 0. Okay, so this is the orientation, and the part of the unit circle is running counterclockwise. Okay, so assume C. Okay, so this is C. C is oriented in the counterclockwise direction. The figure to the right is the plot of the field F, along with the curve C. Using the picture, try to decide if the flow of F along the circular part of C is positive, 0, or negative. Orientation matters here. Yes. See? Let's look at the arrows. Well, my orientation is going this way, but however, my vector field is going that way. What can you imagine? The dot product, because it looks like they go to the opposite direction, so the dot product will give us negative, so the answer will be negative work done. I mean flow. Okay, so work done is for force, but if we have fluid, then we have circulation or flow. Okay, part B, using the picture, try to decide if the flow of F along the straight line is positive, 0, or negative. Well, because it looks like they go to the same direction almost, then we kind of expect the dot product will be positive. Which of the two quantities from A and B will be greater in absolute value? Okay, now let's see here. Which one is greater? Let's see here. Let's look at the, oops, sorry. Okay. So here, we look at the blue one. You can see on this side, the vector field is small, but on this side, the vector field is big. Okay, so if we look at the magnitude of it, well then here, because the vector field has more longer arrows, so we kind of expect this guy, the magnitude of the dot product will be bigger. So the two quantities from A and B, A will be bigger. I know it's negative, but the magnitude is bigger. So far, so good, everybody? Do you agree? Okay, using your guesses so far, decide the circulation of F along the whole curve is positive, 0, or negative. Well, because part A is negative, part B is positive, and we know the magnitude of part A is bigger, so we guess the answer should be negative. Okay, that's our guess. Okay, now let's calculate. So the formula for the fluid velocity field is actually x squared minus xy. Okay, so with two coordinates. Verify our guesses from part A by setting up and evaluating the appropriate line integral. That is to compute the flow of the vector field F along the circular parts of the path. Okay, first we need, so let's call this a C1. Let's call this a C2. And we are looking for C1. Can you find a parameterization for C1? So, unit circle, what is the natural parameterization? Cosine t sine t, right? And then, what is the derivative? Minus sine t cosine t, right? And then what is our line integral on the path C1? We use f dot dr equals So here, because it's in the first quadrant, then our t is from 0 to pi over 2. So t from 0 to pi over 2. F. So f is x squared. X is cosine. So we have cosine squared minus xy. So cosine t sine t. Dot. dr will be negative sine t cosine t dt. Alright, so let's calculate the dot products. Cosine squared times minus sine t is minus cosine squared sine t. And then we also have minus cosine squared sine t dt. And what is that? Well, we can combine them. We get negative 2, 0 to pi over 2 cosine squared sine t. Okay, so do you realize that sine is the kind of the derivative of cosine? So here we can do u substitution. Let u be cosine t, du is minus sine t dt. Then this is negative 2 u of 0, u of pi over 2. And then we have u squared. And then sine t is minus u, but minus u will change the in front to be a positive. Okay, so we have 2 and then u cubed over 3. U of 0, cosine 0 is 1. U of pi over 2, cosine pi over 2 is 0. So we get, we plug in 0 first, minus we plug in 1. We get negative 2 over 3. And it's negative, okay? Yeah, we guess it's negative. Because it's like, looks like the orientation and the vector field, they are in the opposite direction. Okay, let's continue. So using the formula, verify our guess from part B by setting up and evaluating the appropriate line integral. So we have the curve, okay, it passed through 0, 1 and 1, 0. So it's from 0, 1 to 1, 0. So to find a parameterization for it, we need to use, this is a line segment, right? We need to find the direction and the points on it. So here, what is the direction? V is, final point is 1, 0 minus 0, 1. That is 1 minus 1. Okay, and then the parameterization is the initial point, which is 0, 1 plus t times this direction vector, 1, negative 1. So we have t and then 1 minus t. So far, so good, everybody? And we know the direction vector, well, this guy is the same as gamma prime of t, right? Then we're ready because the line integral f dot d gamma is, okay, t from 0 to 1, f x squared, well, x is t, so t squared minus x is t, y is 1 minus t, that dr is, so the gamma is 1 minus 1 dt. Then we have t squared minus become plus t 1 minus t dt. Oh, let's distribute it. So we get t squared, is t minus t squared dt. Well, then t squared cancel. Integral of t is t squared over 2, evaluate from 0 to 1. So we plug in 1, we get 1/2. We plug in 0, we get 0. So the answer is 1/2. You see, it's positive. Now, what is the total circulation? Well, total circulation, we just add those two line integral up, right? Minus 2 over 3 plus 1/2. Well, that is negative 1 over 6, right? You can see the answer is negative. So this is the whole path line integral. So far, so good, everybody. And it is so our gas match with our gases, right? Okay, great. Let's continue. Find the work done by the force. So we are now in space. We have a force x, y, z, b minus y, x, z along the helix cosine t, sine t, t from the point 1, 0, 0 to the point 1, 0, 2 pi. Well, this guy corresponds to t equal to 0. This guy corresponds to t equals 2 pi. Right? So what is gamma prime of t? Well, we'll take the derivative of gamma t. So that is derivative of cosine is minus sine t. Derivative of sine is cosine t. Derivative of t is 1. Oh, by the way, sometimes I put gamma, sometimes I put r. different notes. Anyway, we use both of them to represent displacement function. Okay, parameterization. All right, so that is the derivative, the velocity, right? And now we're ready because the line integral equals. So t goes from 0 to 2 pi. F minus y, we have y is sine t, x is cosine t, z is t. Dot product with our velocity dt. Okay, minus sine t times minus sine t is positive sine t squared. Cosine times cosine is cosine t squared. T times 1 is t. Woo! Sine squared plus cosine squared is 1. So we just get 1 plus t dt. So far so good, everybody? Do you have the same answer? And then integral of 1 is t. Integral of t is t squared over 2. Evaluate from 0 to 2 pi. We plug in 2 pi first. Well, then this is 4 pi squared over 2. Minus when we plug in 0 is all 0. And then here we can cancel. So we get 2 pi minus 2 pi squared. Oop, let me see. Oh, it's plus, sorry. So far, so good, everybody. Okay, so that's the work done by a force along a curve, okay? All right. Let's continue in video part C, okay? So I want to spend time to talk about circulation and flux. All right, see you soon.